Hey, welcome everyone. Let's talk about acids and bases. So first of all, what is an acid and a base, and what's an indicator? So I would rather show you rather than tell you all of this. So at the outset, I want to say this red cabbage I got from the store, cut it up and threw it in a pot, boiled it, and that actually will make an indicator. This is something that you can do as well. Let me show you what an indicator does in the presence of acids, most of which you are familiar with. Alright, and so these are a couple follow-up pictures that I took from the video, so you can clearly see the colors that are produced. In the video it may have been a little hard to see, but on the left we ended up with a yellowish greenish color right here. So you get kind of a wide range of colors with indicators in the presence of different acids and bases. So that's the beauty of an indicator, is it makes invisible things visible. So we generally cannot see chemical reactions. They're just too small to observe. But when you have an indicator, you can see the effects of a chemical reaction. And they help us to measure something called pH. You could say, well, what is pH? pH is going to help us to measure how acidic or how basic something is. And there is an equation that goes with this. It is the negative log of the hydrogen ion concentration. So if you're in a chemistry class, you may need to do calculations with that. And what the negative log means, it's a base 10 log. So that means that, like if you were going to compare lemon juice with grapefruit juice, let's say, lemon juice is only 1 point lower, more acidic. This is the acidic side. 7 is right in the middle for pure water, and this is the basic side over here, generally up to 14. But if we were going to look at, say, lemon juice versus grapefruit juice, you could say, well, it's only 1 point lower on the pH scale in terms of lemon juice versus grapefruit juice. Because it's a log scale, though, that would mean the lemon juice is 10 times more acidic than the grapefruit juice. And that would mean, therefore, that the concentration of the hydrogen ions involved are going to be 10 times greater in the lemon juice than they would be in the grapefruit juice. So that's what we mean by the pH scale, and the fact that it's a log scale tells us that we have very wide ranges of amounts of these things. Okay, well that's a little bit about pH, but what is pH useful for? Well, it's useful for measuring how acidic or how basic something is. And so what does it mean to talk about acids and bases? Well, first of all, acids, a few things that you may be familiar with. They give food a sour or tart taste. They change blue litmus paper strips to red. And an example of a food that you've experienced before that would be acidic would be like a lemon, for instance. Whereas bases, they give food a bitter taste and can be slippery to the touch. They also change red litmus paper strips to blue. So this is an acidic solution, so it looks like you're turning to an acid. Here you can clearly see that this is acidic. Now, I just mentioned that some foods taste bitter or taste sour as an example of what we mean with this. You should not go out and taste acids and bases. They can be extremely dangerous. Alright, so let's talk a little bit more about the background you'll need to understand this. When I say a hydrogen ion, an H+ ion, why is it called a proton? Well, on the left you can see what you would see in the periodic table over here. This 1 means we have 1 proton on average. That's what we have, is just 1 proton. Occasionally we have a neutron, so I just included the neutron here. Either way, whether you have the neutron here or not, the neutron doesn't really do anything in these reactions that we're going to be talking about. It's neutral, meaning it has no charge in and of itself, so we can kind of ignore it for these purposes. So this is kind of a diagram of a hydrogen atom, similar to a Bohr model atom if you've heard of those in the past. But let's think about what happens. Well, if it loses an electron, let's say it loses an electron, what would it be called? Well, it'd be a hydrogen ion over here. It's also called a proton because we can ignore the neutron, and basically all we have left of significance for our purposes is going to be the proton itself. So when I say proton, that's what I mean. It's an H+ ion. Alright, so let's talk about that. So the question is, what do acids and bases do chemically speaking? So I'm going to go over 2 different types of definitions of acids and bases in terms of what they actually do. This first one, though, is probably the most common that you're going to see in a high school chemistry setting. So we say for the Bronsted-Lowry definition of an acid, acids are proton donors and bases are proton acceptors. So let me show you what I'm talking about. You can see the reversible chemical equation here. And I want you to think about what each chemical actor is doing. So from ammonia going from left to right, what's going to happen is ammonia is going to gain a proton as it becomes the ammonium ion over here. So this, because it's accepting a proton, it's going to act as a base. Water, in this case, is going to donate a proton. It's going to give away an H+ ion, and so it's going to be acting like an acid. Over here on the right-hand side, you can see that it has a conjugate. Ammonia has a conjugate with the ammonium ion. That means kind of like its partner. And if we start with a base, then its conjugate will necessarily be an acid. One other way of thinking about this, because this is reversible, this ammonium ion, if it was going from right to left, to be able to go from right to left, it would have to be a proton donor, meaning it would have to give off an H+ ion. And if we take a look at water, its conjugate is going to be the hydroxide ion, and since this is behaving like an acid, its conjugate must be behaving like a base. And we can use the same reasoning if we went from right to left over here. Then hydroxide ion would have to accept a proton to go from right to left. And if it accepted a proton, then it would be acting like a base. Let's do one more example over here and you can see what's happening. So the hydrochloric acid on the left is going to be behaving like an acid, you know, because of its name, but more importantly, because as it goes from left to right with its conjugate over here, it's going to be giving off a proton ion. And so it's giving off that H+, which means it's behaving like an acid. Here, if we take a look at water, it's going to be accepting an H+ ion, and so therefore it's going to be acting like a base. And then if you look at their conjugates, well, water is going to be a conjugate with the hydronium ion, and so if that's the base, its conjugate must be behaving like a conjugate acid, and then if this is your acid over here, its conjugate must be behaving like a conjugate base. Now I want you to notice that here water is behaving like a base. In our previous example, water is behaving like an acid. And that's special. Molecules that can do that, either behave like an acid or a base, are called amphoteric. Lastly, there is another type of acid and bases that you can think about. This is actually more general, so in a way it's more useful. I think it's a little bit harder to get used to than the Bronsted-Lowry definition, but it is important for you to be exposed to this. So for the Lewis definition of an acid and a base, acids are electron pair acceptors and bases are electron pair donors. So in this case, if we look at this equation right here, this hydrogen ion is going to accept a couple of electrons as it comes over here to the right, and this hydroxide ion right here is going to be electron pair donors, and so that means this is going to be a Lewis base, this is a Lewis acid, as they come together to form water. So hopefully that was helpful. If you have any comments down below, please let me know. I will put a link down to this entire unit, and I've basically done an entire year of physics lessons to help students learn physics as well. Take care and have a great day.